Section 8.3, introducing laws of logarithms today. So we're going to introduce 3 laws for logarithms, and then we're going to evaluate expressions using laws. So first thing we're going to talk about is the change of base identity. This helps us evaluate logs using technology, because some of our calculators, even though some calculators will allow us to do a log, most of our calculators either do a log base 10 or something we call the natural logarithm. And the natural logarithm was found by the great mathematician Leonhard Euler, who discovered the number e. Similar to pi, we have this number e, and it's calculated, and he calculated its value to 23 decimal places. It is often called Euler's number, and like pi, it's a transcendental number. This means that it is not the root of any algebraic equation with integer coefficients. It's to it as a natural choice as a logarithmic base. The number e is equal to approximately 2.71828182845. So the natural logarithm of x, okay, so you technically we don't need to know how the natural logarithm or the natural e number was calculated. It's a fairly complex process. We just have to recognize that for solving logs, we usually work in a common base of 10 or a natural logarithm. So if we are to write the natural logarithm, this can be written as log e of x. Remembering e is this, represents this number, approximately 2.72, or we'd quite often see this long of x. So when we see this long of x, that tells us that we are working in a base of e. So I'm just introducing this to you. You're not work with a natural logarithm, but it might come up as a base of e. We definitely use it pretty much all the time in calculus, so it's a good introduction. So if I wanted to evaluate logarithmic values, log 2 of 16. So recalling from last, what this means is we take base of 2 and we ask ourselves 2 to what power equates to 16. So hopefully most of us can start to evaluate this just off the top of our heads now. So 2 to the power of 4 equates to 16. So log 2 of 16 evaluates to 4. 2 is going to evaluate to 5, because 2 to the power of 5 equates to 32. So the issue is when we have a base and it evaluates to a value that is outside of a whole number. So for example, log 2 of 20. I could probably estimate this value, because 20 falls between 16 and 32, so it's going to have an answer between 4 and 5. My guess is I'm going to guess, this is an estimate, that it's 4.3. Now, in order to find the exact value, because some of our calculators do not work in a base other than 10 or a natural logarithm, we're going to introduce this identity called the change of base identity. And what the change of base identity allows us to do, it allows us to evaluate logarithms like this by changing the base of it to any base that we want. So the change of base is the following. If you're given log base some value b of c, that can be rewritten as a division statement by taking log of introducing a completely different base, a, of c divided by log base a, the same of the b value. So if I wanted to evaluate log 2 of 20, I can change this to a completely different base, and I'm going to choose to change this to a base of 10, so that I can now use my calculator to evaluate this. So remembering, if there is no base written, then that's always a common of 10. So technically what we're doing is we're taking a log base 10 of 20, and we're going to divide it by log base 10 of 2. So now on our calculators, our log button is here. So this is our log base 10, and you'll also see this button ln. This is our natural base. So in order to evaluate, I could change my base into a log base 10 divided by log of 2. If you notice, we have just a common, if you notice, we just have a comma here, and I get approximately 4.32. So my estimate was pretty close. Okay, or to use my calculator, I could have changed this to a log base e, a natural logarithm. But technically a log base e can be rewritten as just log of 20 divided by log of 2. It's like a short form. So if I take log of 20 now and divide that by log of 2, I should get the exact same answer, 4.32. So the change of a base identity allows you to change the base of any logarithm to any base that you want in the world. So it doesn't have to be a 10 and an e. But if you were working with or trying to evaluate something and trying to evaluate it on your calculator, you'd want to use that common base or natural base simply because that's what your calculator works in. Okay, so that's your change of base identity. We're now going to introduce our laws of logarithms. And so just like exponents, the exponent laws, we have laws for logarithms. So there's 3 laws that we have to remember. I believe these are all on your formula sheets. The product law, so if we take a log base a, so any base, and we're multiplying 2 values together, that could be rewritten as log base a of m plus log base a of n. So we can like separate these values by adding the 2 logarithms with the same base. Quotient law, similarly, log base a, if we divide 2 values in that logarithm, we can separate those values by taking a log base a of m minus log base a of n. And lastly is our power law. If we take a log of m and that m value is taken to a higher power of n, that can be rewritten as where this n value in front of the logarithm and becomes a multiplication statement, n log a of m. Okay, so we're going to work through some examples using these laws of logarithms. So, for example, we want to evaluate the following using laws of logarithms. So what we want to do is, I don't want to get this into my calculator, I actually want to use my laws of logarithms to simplify and then evaluate. So I'm going to rewrite this as a single logarithm with a base 6. So because I see this plus sign, I could rewrite this as a log base 6 of 4 times 9. 4 times 9 gives me 36. So log base 6 of 36. Now I can evaluate this. 6 to what power equates to 36? This should evaluate to 2. Okay, moving on. If my 2 logarithms are being subtracted, I could rewrite this as log base 5 of 500 divided by 4. So recognize this is your value that's now part of this single logarithm. 500 divided by 4 gives me 125. So to evaluate this now, 5 to what power equates to 125? That should equate to 3. Lots of these you should be trying to do them without your calculators. It just makes your life a little bit easier to do that practice forward. Okay, so when we see something with 3 logarithms, you always want to work from left to right. So I'd want to divide these values first before I multiply. So I'm going to rewrite this as log base 8 of 6 divided by 3. 6 divided by 3 is 2. So now I'm going to multiply my 2 values. 2 times 2 would give me 4, so this equates to a log base 8 of 4. So this one's a little bit trickier to figure out. So in order to solve this, to evaluate this, I'm going to say 8 to what power equates to 4. Now I'm going to solve this exponential equation by getting these as common bases of 2. So this would be 2 cubed, so 2 to the 3x is equal to 2 squared. I'm now going to ignore my bases, so I have 3x equals 2. So 8 of 6 minus log 8 of 3 plus log 8 of 2 would evaluate to a value of 2/3. Okay, so a way to check that is you could change each of these into a change of base formula with your common base or a natural base. So I could rewrite this as log 6 divided by log of 8 minus log of 3 divided by log of 8 plus log 2 divided by log of 8. On your calculator, if you wanted to evaluate this, just to double check your answer, I would take a log of 6 divided by log of 8 plus log of 3 divided by log of 8 plus, oh sorry, this should be a minus, plus log of 2 divided by log of 8. So when I do that, all of that should equate to 2/3, which we can see it does. Okay, so we get 2/3. Okay, so one way to check your work is by using that change of base identity and rewriting this as a common logarithm. All right, following 2 log 3 of 12 minus 2 log 3 of 4. So lots of ways you could do this question. I'm going to apply my power law first, each of these values. So my power law says that if my logarithm is multiplied by some coefficient, I could rewrite that as moving that coefficient as the exponent on the 12 and the exponent on the 4. So I'm going to evaluate those. So 3 squared gives me 144. 4 squared is 16. So this minus value is our quotient law. So now I'm going to rewrite this as log 3 of 144 divided by 16, which gives us a value of 9. Okay, and then I can say, well, 3 to what power equates to 2? Your answer is 2, so it equates to 2. Okay, so lots of different ways of doing this type of question. Another way of doing it, I could have factored out a 2 out of my logarithms to start. Then divided, so 12 divided by 4 gives me 3. And then I could have just evaluated this before I multiplied by 2. So 3 to what power equates to 3? Well, 3 to the power of 1 equates to 3. 3 times 2 equates to 2. So a couple different ways to solve that equation. You end up with the same answer regardless. All right, and then moving on to E here. I'm just going to erase this area just so I have some room here. All right, 1/2 log of 144 minus log 3 of 4 plus 2 log 3 of 3. So in this case, I definitely can't factor out a common logarithm, so I'm kind of forced to use my power laws here. So your power law should be the first step that you should be looking for before you do multiplication or division, right? Technically, you should be doing exponents before you multiply or divide. So we got to use our power law first. So I'm going to rewrite this as log 3 of 144 to the exponent of 1/2 minus log 3 of 4 plus log 3 of 3 squared. Well, technically 144 to the 1/2 could be rewritten as the square root of 144. And then a minus expression means I'm going to use the quotient law, so technically that's going to be divided by 4. And then we have this log 3 of, and I'm going to evaluate 3 squared, which gives me 9. All right, so now I'm going to take the square root of 144, which is technically 12. And then this plus means I'm going to multiply it by this value. So I got to multiply that all by 9. So 12 divided by 4 is 3. So log 3 of 3 times 9, we get log 3 of 27. 3 to what power equates to 27? This is all going to evaluate to 3. Okay, so as you can see, we're kind of using here with logarithmic laws. We got to be fairly good at those expressions. Okay, and recognize with numbers is fairly straightforward, but eventually most questions that I've seen on the diploma with logs and exponents, they usually throw in variables for you. So you're not actually working with numbers, you're working with variables. Similar to example 2, write each as a single logarithm. So if I want to write these as a single logarithm, I need to combine all 3 of these logs into 1. If you notice, there is no base written, so that tells me I'm working in a base of 10. So again, you always want to apply your power law first. So this becomes log A minus log B cubed plus log of the 5th root of C to the power of 5. Well, technically root 5, the 5th root of 5 to the power of 5, these are just going to cancel each other out and we end up with a C value. So then working through, we'd want to divide these values first. So we get a log of A over B cubed plus log C. And then we're now going to use our product law. So this would be log of A times C all over B cubed as your final single logarithm. Okay. All right, similarly, given log base 7 of cube root of x minus log base 7 of y cubed plus log base 7, or 2 times log base 7 of y. So once again, I'm going to apply my power law first. So this becomes log base 7 of y squared. I am now going to divide these values first. So this is why you got to do order of operations, because some people might look at this and say, oh, I'm going to multiply these first to get a y to the power of 5, right? Multiplying. But technically, I need to divide these first and then multiply. So this actually ends up to be in my numerator as opposed to my denominator. So I'll show you what I mean. So this is cube root of x over y cubed. And then I need to multiply that, right, because this is our product law, times a y squared. So technically what's going to happen here is, because technically this is over 1, these y squareds are going to cancel with 2 of those, and I'm left with log base 7 of cube root of x all over y. All right, example 3. If log base 3 of 4 is equal to x, express the following in terms of x. So I want to write this as an expression of x as opposed to evaluate it. So it tells me that log base 3 of 4 is equivalent to x. So what I want to do is I want to write this in terms of a log base 3 of 4. So what I'm going to do is I'm going to rewrite 64 to a different base. So it's written as a base of 4 here. So I could rewrite this as log base 3 of, instead of 64, I'm going to write that as 4 equates to 64. Now using my power law, I can rewrite this as 3 log 3 of 4. And now I can have this log base 3 of 4. This entire expression of logarithm can be replaced with x. So what is my expression in terms of x? Would just be 3 times x. And that would be my final answer. Okay. All right, similarly, log base 3 of 144. So the first thing I'm going to check is, well, can I change 144 to a base of 4? So 4 cubed, I know is 64. 4 to the 4th, 256. So I can't write 104 to a base of 4. So now what you want to think about is, well, can I change the look of this at all? Well, 144, lots of different ways. So I might want to rewrite this as a product of two numbers. So if I divided this by 4, I get a 36, right? So I'm trying to break down this expression. So the other way I can think of this is, well, technically 144 is equivalent to 12 squared. There's lots of ways you can get to your final answer. If I rewrite this as my power law, I get this. And now I'm going to break down the 12 as a product of two numbers. And technically the numbers I want are a base of 4, but I'd also want something that I can evaluate as a base of with this base of 3. So I'm not going to change this to a 2 times 6. I'm going to change this to a 4 times 3. Now I can rewrite this using my product law. Remember, this 2 needs to be multiplied by this whole thing. So this needs to be in a separate set of brackets. So I have log 3 of 4 plus log 3 of 3. All right, so now I'm going to go and evaluate inside my square brackets. Well, log 3 of 4 is going to equate to an x, right? Log 3 of 3 equates to a value of 1. I can actually evaluate that because 3 to the power of 1 equates to 3. So then what is my expression in terms of x for this logarithm? 2x plus 2, or you could leave it in factored form. I don't think it would really matter. All right, and then lastly, simplify the expressions below and then state any restrictions on x. All right, so if we were to simplify divided sign, we're going to take a log base 7. This needs to be rewritten as 2x minus 2 over an x squared plus 2x minus 3. That's our quotient law. How do I simplify this? Well, thinking back to our rational expressions unit from Math 20, I'd want to factor the numerator and denominator. So I'm going to factor out a 2. In my denominator, I can factor this to be an x plus 3 and an x minus 1. Those are going to cancel. So my simplified expression would be a log base 7 of 2 over x plus 3. Okay, and then it says to state any restrictions on x. Okay, well, restrictions on x, this base, remember, always has to be greater than 0, but so does this expression within our logarithm. This also has to be a positive value. So our restrictions would be the following. 2x minus 2 would have to be a value greater than 0, not equal to, can't equal 0 either. Also, x squared minus, plus 2x minus 3 would also have to be greater than 0. So this is a linear inequality which we can just simply solve. So x would have to be greater than 1. Here, to solve a quadratic inequality, a little bit trickier, This takes us back to our Math 20 course. And how do you solve a quadratic linear inequality? Well, we want to set up what we call a interval chart. Okay, so the factors of this would be an x minus 3 and an, if I were to solve this for x, I'd get a 3 and a negative 1. So I want to test all the intervals that's outlined to these values. So I'd want to test all the values less than negative 1. I'd want the values greater than negative 1 but less than 3. And then I'd want to test all the values that are greater than 3. So what I'm looking for is I'm looking for whether that function is a positive or negative. And if the function is positive, then that would be the values that we'd want for x, and then anything other would be just. So if I substitute in a value smaller than negative 1 into this expression, so let's say, oh sorry, I factored this wrong. There should be a plus 3 and a negative 1. This should be a plus 1 and a negative 3. So let me just change this up quickly, sorry. This should be less than negative 3, less than negative 3, greater than 1, less than 1, and greater than 1. So if I substitute in a value smaller than negative 3 into this expression, let's say a negative 4, negative 4 minus 3 would give me smaller than negative 3 again here would give me a negative. If I multiply these two values, because that's what we're doing here in our factored form, we're taking this expression times this. Negative times a negative is a positive. One of our restrictions on x tells me, so if this gives me a positive value, then x has to be less than negative 3. And then this tells me that negative 3, between negative 3 and 1, let's pick a value of 0, I'd get a negative. 0 minus 3 would be a negative. Oh, sorry, this should be a plus 3. So this is going to be a positive. This is going to be a negative. This is going to be a negative. So this is what we don't want. And then lastly, greater than 1, this would be a positive. A positive. Positive times a positive gives me a positive. What are my restrictions on x here? This restriction says x has to be greater than 1. This tells me for this expression has to be less than negative 3, but greater than 1. So I have these restrictions. For this expression, I have this restriction. But if I want to talk about the entire expression, what would be my restriction for the entire expression? Would be simply x has to be greater than 1. Even though